welcome again to the new lecture of this course, Fundamentals and Applications of Dielectric Ceramics. So, we will just briefly do a recap of what we did in the last lecture. So, in the last lecture we looked at effect of impurity addition. So, effect of impurity addition, generally impurity addition leads to formation of a extrinsic region when you plot concentration versus temperature. So, generally at lower temperature you will have extrinsic region where defect concentration is independent of temperature, okay. And at higher temperature you will have intrinsic region where n will be a function of temperature, and generally the plot will look like this. So, if you have log n as a function of 1 over T, so this is the higher temperature region, this is the lower temperature region. So, this would be your extrinsic region and this would be intrinsic region, okay. And this is also reflected in properties such as conductivity and diffusivities and things like that, where you will see that because of constant defect concentration the conductivity also remains constant as a function of temperature, because conductivity is proportional to n. So, as a result, despite having some dependence on temperature, it virtually remains constant up to certain temperature because of higher defect concentration, because of constant defect concentration which is high. And then we looked at the defect equilibrium. So, basically we wanted to establish conditions as a function of ambient conditions. So, when in the case of stoichiometric solids or stoichiometric defects, the concentration of defects is basically dependent upon temperature only, it does not depend upon the conditions like partial pressure of oxygen, etc. And the denominator, whether you will have 2 kT or whether you will have 3 kT, 4 kT or whatever, it will depend upon the stoichiometry of oxide. So, for MO it would be 2 kT, but for M2O3 and MO2 it could be different. So, let us now further dwell upon the same thing. We were looking at the defect equilibrium in non-stoichiometric So, we are looking at the case of oxygen deficient oxides, okay. So, basically it is a case of either MO1 minus delta or M1 plus delta O, okay. So, let us say the first case which is when oxygen vacancies are dominant defects. So, if the case is example is of MO, then the defect reaction can be written as, so oxygen at oxygen site goes out, okay, leaving at, so metal at metal site will remain. So, if you just write in a more, so metal at metal site remains at metal site, which means metal sites are conserved. Oxygen site, to maintain the site conservancy, will become empty. So, this will become VO and the compensating defects will be 2 electrons if you consider electronic concentration, okay, compensation, okay. So, so this is assuming electronic compensation. If you consider ionic compensation, you will not form electrons, rather you will have reduction of metal ions, okay. So, that is what is going to happen. So, basically now if you want to write down the defect, so you can basically write down the reaction constant. So, let us say this is a, let us write the reaction constant, which is equal to PO to the power half into VO. We can ignore mm because mm is cancelled on both sides. So, we can ignore mm into, if I say electron concentration as Ne, it becomes Ne square. Okay. So, it becomes a product of vacancy oxygen vacancy concentration multiplied by electron concentration square multiplied by PO to the power half, and here we are assuming that OO is equal to 1. Okay. So, we assume that OO is equal to 1, which is basically the case of ideality. And to maintain the electrical neutrality, what is the electrical neutrality condition? The electrical neutrality condition is that for every oxygen vacancy we are creating 2 electrons. So, which means Ne is equal to twice of, okay, this is electrical neutrality. All right. So, when you write this and if you substitute this in the above equation, it becomes, so K will become PO to the power half into VO into 2VO square. Okay. So, if you now just rearrange it, this K will become equal to 4 into VO to the power 3 into PO to the power half. So, I can write this as now VO being, if I just want to express VO now, so this becomes K divided by 4 to the power 1 by 3 into PO to the power minus 1 by 6. So, of course, K can be written from the usual free energy reaction, and this will become some K1 into exponential of minus delta H by KT. So, temperature dependence will be inbuilt here, but what is important here is, in addition to dependence upon temperature, this is temperature dependent, because K will show the temperature dependence, but this is additionally what we see is oxygen, partial pressure of oxygen dependence. So, what this shows you is that as you increase the partial pressure of oxygen, the vacancy concentration will go down, and as you decrease the partial pressure of oxygen, the vacancy concentration will go up. So, now when you plot this, so when you plot VO, so you can plot this as a function of sort of log plot, semi log plot. Okay. So, let us say log of VO, PO2. So, the vacancy concentration will decrease as a function of PO2, and this will have a slope of minus 1 over 6. You can also plot on the same plot the electron concentration Ne, which is twice of VO. So, basically this line would be, it will run parallel, right. So, this is Ne, which is twice of VO. So, this is what we see, that in case of non-stoichiometric oxides, in addition to temperature dependence, which will be similar to what you have. So, at a fixed, so this is at constant temperature. Okay. So, at a constant temperature, the vacancy of oxygen vacancies and electron concentration will go down as you increase the partial pressure of oxygen. So, basically as you reduce the partial pressure of oxygen, you will make oxygen more and more oxygen deficient, and you will create more and more vacancies and consequently electrons in the system. That is how you make a defect prone oxide. Okay. Right. No, why should Ne be constant? Ne Ne is twice of VO. So, for every vacancy you create, you are creating 2 electrons. So, as you increase the vacancy concentration, the electron concentration will also increase or decrease as depending upon the condition. Okay. So, this is the condition when you have oxygen vacancies present. Now, let us see what will happen when you have when metal interstitials are dominant. So, when metal interstitials are dominant defects, then we can write MM plus OO as Mi, oxygen goes out. So, this will be half O2 plus we will create 2 electrons, all right. So, we have site valence, the metal has lost its site, gone to interstitial site, oxygen has lost its site, gone out. So, we are basically, so these 2 sites are destroyed, right, to maintain site ratio, right. Okay. So, for one oxygen site destroyed, you will have to also destroy the metal site, that is why it becomes metal interstitial. So, now when you write the defect reaction for this is K is equal to Mi PO to the power half into Ne square, and we can take these okay, considering ideal situation, especially when Mi is Mi is very small as compared to and OO, okay, because there are more metals and oxygens than interstitials. And what is the electrical neutrality condition? That says that Ne is equal to 2 Mi, okay. You are creating 2 electrons for every metal interstitial. So, now you can do the maths yourself. You will have, so if you do this substitution, you will have Mi being equal to K divided by 4 to the power 1 by 3 into PO to the power minus 1 by 6, and this is equal to Ne divided by 2. Okay. So, again you can plot make the plot, and the plot will be similar to the previous plot, where you can plot Me and I both on log scale as a function of PO2, and as you increase the PO2, the metal interstitial concentration will decrease, and this is the electron concentration, this is N and this is Mi, all right. Now, a little tricky one, the tricky one is what happens when both of them are present. Now, the previous cases could be when vacancy formation energy is very low as compared to metal interstitial energy, or metal interstitials form very easily as compared to vacancies. Now, there could be situations where both the energies are sort of comparable, okay. Then there is a possibility that both of them could be present, and this is, for example, in TiO2 or even in niobium oxide, these are scenarios. So, let us say we take a case of MO2. Okay, we do not take a case of just to reflect the oxide, we take a case of MO2. So, if we take a case of MO2, in case of MO2 we will have oxygen vacancies as vacancy defects, and we will have metal interstitial, which will be 4 positive charges interstitials. Okay. So, for every metal interstitial, so you will consider for charge valence for every vacancy, for every metal interstitial you will have 2 oxygen vacancies, right. So, let us say we have defect reactions. So, we write the defect reactions for oxygen vacancy. Okay, let me just I think use a different color. So, for oxygen vacancy, we first write as oxygen at oxygen site goes out of system. This creates a vacant oxygen site, plus this gives rise to 2 electrons. For metal interstitial, I can write this as MM plus 2OO. So, Mi plus O2 plus 4 electrons. Okay. You can write the same thing for MO also, and considering that OO is equal to MM is equal to 1, they are very large in number as compared to defects. We can write the defect reactions as, so if I take this as 1, this as 2. For 1 I can write K1 as VO into Ne square into PO2 to the power half. K2 I can write as Mi into PO2 into Ne to the power 4. Okay. Now, what is the electrical neutrality condition? Ne will be equal to now 2 VO plus 4 Mi, right, depending upon which one dominates or it has to be balanced, right. So, this will be the electrical neutrality condition. So, you can consider cases when, so the first case is when, so limiting cases, so we consider limiting cases, right. Limiting conditions will be when VO is very large as compared to Mi, or it could be when Mi is very large as compared to VO. Okay. So, if we consider these limiting conditions, then limiting condition, let us say the first one is VO is larger than Mi, then this is simpler. We can write this half Ne is equal to VO is equal to K1 divided by 4 to the power 1 by 3 into P to the power minus 1 by 6. This is straightforward. This you will have to work out a little. When Mi is greater than VO, then you will have to go to, so when Mi is greater than VO, then Ne is equal to 4 Mi. Okay. So, Ne is equal to 4 Ni, you will have to substitute it there. So, it will become 4 to the power 4 into Mi to the power 4, right. So, basically it will become Mi to the power 5 if you multiply by this Mi. So, it will become, so Mi will be equal to Ne divided by 4. This will be K2 to the divided by 4 to the power 4 to the power 1 by 5 into PO to the power. If you now look at this expression, this was PO2, this will become PO to the power minus 1 over 5, right. So, you will have to basically, so this will be K2 into Mi to the power 5 into PO2 into 4 to the power 4, all right. So, this will become K2 divided by 4 to the power 4, 4 to the power 4 is 256 basically. You can write this as 256 just to avoid any okay, minus 1 over 5. So, this is what you will have situations like. So, you will have Mi showing a dependence of minus 1 over 5 and oxygen showing a dependence of minus 1 over 6. So, now in both of these regimes you would like to calculate what is the corresponding metal interstitial concentration and what is the corresponding oxygen vacancy concentration. So, for the first case, so let us take the first case. The first case was when VO was much greater than Mi. Okay. So, in the first case we calculated half Ne is equal to VO, which is equal to K1 divided by 4 to the power 1 by 3 into P to the power minus 1 by 6. So, we have got the expressions for Ne and VO, but we do not know how the Mi is going to vary in this regime. So, Mi is written using the Mi formula. So, Mi formula is basically the second equation, which is this equation. So, Mi is equal to K2 into Po to the power minus 1 into Ne. So, if you basically you are writing this expression, this one, second one. So, this will become Ne to the power minus 4. Ne to the power minus 4. Now, you substitute the value of Ne from this expression. So, this will become K2 into Po to the power minus 1 into Ne now is 2 into K1 divided by 4 to the power 1 by 3 into P to the power minus 1 over 6, and this is all equal to minus 4. Okay. So, then we work out these expressions and we will see this is K2 P to the power minus 1, this is, so you can just modify this as, so this 2 can go 2 will be 8 to the power 1 by 3. So, this could be so if you take 2 inside it will become 8, right, and 8 divided by 4, this will be 2 K1 to the power minus 4 by 3, and this will be equal to Po to the power minus plus 4 by 6. So, basically this will be K2 divided by 2 K1 into 4 by 3 into Po2 to the power minus of, so this is 2 over 3, this will be minus of 1 over 3, all right. So, for the first case when oxygen vacancies dominate over meta-interstitials, then your Mi goes as Po to the power minus 1 by 3 and oxygen goes as, and oxygen vacancies go as minus 1 over 6. For the second case, when Mi dominates over VO, okay, when Mi dominates over VO, we calculated the expression for Mi. So, Mi was equal to Ne divided by 4, and this was equal to K2 to the power 256 into 1 to the power 1 over 5 into P to the power minus 1 over 5. So, let us say K2 divided by 256 to the power into Po to the power minus 1 over 5. Now, we would like to calculate what is VO in this case. So, VO in this case can be calculated using the first equation. The first equation says that VO is equal to, it says that VO is equal to K1 into Ne to the power minus 2 into Po to the power minus 1 by 2. So, this will become K1. So, you replace Ne from there, Ne is now 4 PO to the power minus 1 over 5 to the power minus 2 into PO to the power minus 1 over 2. So, this will become K1 divided by 4, basically it is divided by 4 square. So, 4 square will become 16, K1 divided by 16, alright, and you take this as PO to the power minus 1 by 2 plus minus plus 2 over 5. Okay. So, this will become 2 over 5, this will become minus 1 by 2. So, essentially you have minus 1 by 2 plus 2 over 5. So, this will be K1 divided by 16, sorry K2, where has K2 gone, hang on, we made some mistake here. Yeah, the mistake is this. So, this is VO. So, what we can do is that we can just write this K2 divided by 256 as K1, let us say K2 prime, okay, some value K2 prime. So, K2 prime is equal to K2 divided by 256 to the power 1 by 5, okay, just to make it simpler. So, this is K2 prime. So, this will become K1 divided by K2 prime to the power 2, okay, now it has become okay, and this is PO2 to the power minus 1 by 5, minus 1 by 5 into minus 2, it will become 2 by 5. So, minus 1 by 2 plus 2 by 5, how much this will be? Minus 1 by, so basically this is minus 5, this is plus 4, this will be minus 1 over 10. So, in this regime oxygen vacancy has a dependence of minus 1 over 10 and Mi has a dependence of minus 1 over 5. So, this is how now when you want to make a plot of these and the n will follow the basically the dominant defect, whether it will follow VO or it will follow Mi. So, if you now want to plot this log of, let us say, defect concentration, it's if I just write as n, okay, and then I write it as PO2, okay. So, I see that the defect concentration, so let us first plot the oxygen vacancy concentration. The oxygen vacancy concentration goes as PO to the power minus 1 over 6, okay, and then it goes as PO to the power minus 1 over 10, okay. So, PO to the power minus 1 over 10 is obviously, so let us first draw this when oxygen vacancy dominates, then let us say minus 1 over 6 the first case. So, the magnitudes will of course depend upon the value of K1 and K2 and so on and so forth, but generally the trend would be something like this. So, so we saw that in a certain regime the oxygen vacancy concentration goes as minus 1 over 6, okay. Then the oxygen vacancy concentration is minus 1 over 10. So, initially it is minus 1 over 6 and then it becomes minus 1 over 10. So, this is minus 1 over 6, this is minus 1 over 10. So, this is for let us say VO, okay. The Mi, if you look at the variation of Mi, the Mi in this case goes as minus 1 over 3, okay. So, when oxygen vacancy goes as minus 1 over 6, Mi goes as minus 1 over 3. So, Mi would be something like, if I use a different color, this would be Mi, okay. So, this will go as minus 1 over 3. So, this is Mi, and if you look at the second region, in the second region the Mi goes as minus 1 over 5. So, it will go sort of in this fashion, minus 1 over 5, and the electron concentration in the first case it will follow this line, in the second case it will follow this line. In the first case it will go as minus 1 over 6, in the second case it will go as minus 1 over 5, okay. So, this will be the line of Ne, okay. So, that is how the electron the impurity concentrations will vary when you have mixed effects. There will be crossover regime, and it is not perfect. There may be this region can be even more complex, okay, the crossover region, but this is how the roughly the variation of defect concentration will be as a function of partial pressure of oxygen when you have mixed presence. Okay. So, what we have done in this class is we have looked at the variation of defect concentration as a function of partial pressure of oxygen when one particular defect dominates, and what happens when two defects coexist together. So, we will elaborate upon this further in the next lecture. Thank you.